This is the Step Support Foundation module assignment 3. I'm going to go quite quickly through this because the last video was way too long. So yeah. Question 1. So if you've not seen the Sigma notation before, basically it's like a for loop if you've done programming, and you go through and you sum each one up, starting from n equals 0 to 6 inclusive. So it looks something like this. So you just plug in from values from 0 to 6, and then you just evaluate them all. You can use some knowledge of like the trig function. So this is going to be the same as this. Same with this root 3 over 2 and this root 3 over 2 and then this 1 and 1. Anyways, just solve it, sum it together, you get 2 plus root 3. We've got this series here, Sn, okay, and we're using the same like idea as this with the sigma, and we want to simplify r multiplied by this subtract just that itself. So if you just write out this series, it looks something like this, and then the last term is going to be r to the n minus 1, and if you multiply it by r, what you're doing is you're basically shifting it all. So you're moving all of this to the left, kind of, and you're cutting off this r equals 0 term, and then instead of, you'll have r to the n minus 1 plus 1, so it's just r to the n. Okay, now how do you subtract this from this? Well, the way that I thought about it was, this here is the same as this, except this doesn't have an r to the 0, and this one has an r to the n. So this has a term higher than this one. So if we do this sequence here, subtract this extra term at the end, but then adding this r to the 0 that it doesn't have, you'll get s to sn, so like that, and then just rearrange to get this, and you'll get that as your answer. And then what was it? Okay, I just factorized and then rearranged it like that. Now this is the sum of the sequence Sn, if you've not seen this before. And now when r equals 0, well, when the common ratio is 0, you're going to have every single term in the sequence just be equal to itself, because it'll be 1 multiplied by the one before it. So it's just 1 multiplied by 1 multiplied by 1, all the way down. So it's an arithmetic sequence, and then the sum of the number of terms in it is just how many terms there are, which will be n terms. And to get a formula for this, we're just going to do the exact same thing. So we've got this, we're going to write out a bit like this, but with an a in front. And then I've just written the same thing over here. Step is about using things that they've just shown you, or like kind of told you to use, hinted at you to use, in the next part. So what we're going to do is we're just going to multiply by r, by whatever the common ratio is. We'll use the exact same intuition here, but here, so we can like relate these two series. We'll get this. R to the 0 is just 1, so this is just becomes a. And then I've just gone ahead and simplified this, factor out the a, and then I'm going to factor out un from there, and then just rearrange to get this, and that's fine for that. Now as n gets very large and r to the n, so now r can be some value like a half for this next part, because if it's between 1 and minus 1, it's just going to be some fraction. It doesn't matter what the fraction is, but it'll just be some fraction. So say it's a half, right, and we're raising that to the power of n. Well, the limit, as this is just 1 over 2 to the n, by the way, if you do the limit as it approaches infinity or just gets very large, this will just go to 0, because the numerator grows quicker than the the denominator grows quicker than the numerator. So r to the infinity here is just going to be 0. That's a multiplied by minus 1, so you get this. Multiply both sides, top and bottom, by minus 1 to get this, and that's your final answer. Sorry about the background noise, by the way. There's just detailers in today. Anyways, hopefully it's not too distracting. You've got this here. Now to evaluate this, we've got a is 3. So we're just using the formula that we made. A is 3. R, the common ratio being a half, and then we're going from I equals 0 to 9. Now between 0 and 9, you're counting 10 because you're including 0. So that's why n here is 10. A is 3. R is a half. That's fine. You plug in, you get this. Find the area underneath this graph. If we graph y equals 2x plus 1, it's got a positive gradient. It looks something like this. Gradient 2 and y-intercept 1. So it looks like this. Now, if you just find what this coordinate is, so when x equals 0, when y equals 0, sorry. So this, you get this as a half. This here is obviously just 1. And now we want to go between 2 and 5, so it's roughly here and here. Now, between here and here, it's just a trapezium. So to get the height at this, just plug in x equals 2 into there, and then plug in x equals 5 for this height. Just go ahead and do that. You'll get this. Plug it into the formula for the area of a trapezium. You know how to do this. Height here is just this horizontal distance, which is 3, and you'll get 21 square units. We're being introduced to the floor notation here, where it's this like square bracket. And what it does is it just truncates, so it just gets rid of everything after the last non-decimal. So it gets rid of everything after the decimal point, basically, regardless of whatever that number is. So like 3.14 will go down to 3. Root 25 is going to be 5, so root 24 will probably be like 4.8 or something. So maybe 4.5, I don't know. Either way, it's going to truncate down to 4, and then 5 becomes 5. 10.2 obviously becomes 10. Root 70 is around 8.5 maybe, because it's between 81, which is square root 81, which is 9, and square root 64, which is 8. So it's like 8.5 maybe. That truncates down to 8, and then 10 pi is, oh no, sorry, 6 is just 6, obviously. 10 pi is like 31.4, that truncates down to 31. If x is between 3 and 4, 3 inclusive, it's going to be like 3 point something. Whatever it is, it's just going to round down to a 3. Now, sketch the graph of y equals floor x. So if we just, draw this on. Now, we're using this idea here, but now between 0 and 1, it's just going, excluding 1, it's just going to truncate down to 0. It's just going to round down to 0. So we're going to have like this flat line here. Now, between 1 and 2, excluding 2, but including 1, you'll have like 1 point something. That'll just, be 1. Right, so it's just 1 times whatever the x-coordinate is, so it's just going to be a flat line, excluding 2. Now, including 2, so including 2, but excluding 3, between 2 and 3, it's going to be 2 point something, whatever it is, it's just going to round down to 2, so it'll just be 2, there. And then, between 3 and 4, it'll just be the exact same thing. Okay, so you'll get something like that. Now, now we want to integrate it between 0 and 4, so we've got this here. Now, when you integrate, it's the area underneath the curve, as we've already said. And this is just a bunch of rectangles. So this has a width 1, width 1, width 1. Height is just going to be, we'll just plug in when x equals 1, you'll get 1. This is height 1, this is height 2, this is height 3. So you add that all together, you'll get 6. Now, y equals x floor x. Okay, I've done a table of values and I've just, filled it in slightly. You know how to do this. And if you draw it like, say, axis like this, right? Between 0 and 1, it'll just be 0, obviously. And now, say if you had like 1.5, that'll truncate down to 1, right? But your x value is still 1.5, so it's going to be 1 multiplied by 1.5, right? So as the x value increases, it's just going to be 1 multiplied by the x value. So it's going to like be something like this, right? But it's going to be discontinuous compared to this 2 here, when x equals 2. Now, it's going to be the same idea here, and it's going to look something like this. So between 2 and 3, it'll just truncate down to 2. So it'll just be 2 multiplied by whatever the x value is, and it's going to have a steeper gradient than what it did here, right? So it looks something like this. Okay, now to integrate this, it's just the area underneath the curve. Just, the formula for the area of a trapezium is just a plus b. So a plus b divided by 2 times by height. Yeah, literally just do that. So this is just going to be 1 plus 2 divided by 2 times by height, which is 1. Same thing here. You'll get 6.5 square units. Now this is the step question. So we want to sketch the graph of y equals square root of floor x. Be careful, the floor is inside and outside. I did a table of values. You get something like that. Now, I wrote out the square numbers at the top here. And one thing that I wanted to say is, if you look at like what's in between it, so between 1 and 4 you'll have 3, and then you'll have 5, and then you have 7, 9, 11. So it goes 3, 5, 7, 9, 11, 13. Now that's a really predictable pattern, but it's really important compared to what I'm going to show you just now. So if what have I done next? Okay, so I've just said like between 0 and 1 it's going to be a flat line, obviously. Now between 1 and 2, if you think about it, okay, well, square root 2, but we don't know what square root 2 is. Okay, actually no, it'll just be whatever the x value is, so 2 here, and then you truncate 2, so you floor 2 just to get 2, and then you'll just square root that, so it's just going to be a straight line there between 1 and 2. Okay, and here, like, we've got the idea that it's going to be another flat line between 2 and 3, but the idea is, well, where is it going to be? What's the y value of it going to be? Now here we're square rooting, but here where you were squaring, when I was showing you this, now when we were squaring, the difference between two adjacent terms, they were actually increasing. So this goes from 3, and then 5, 7, 9, 11, 13. So it was increasing. But when you're square rooting, it's kind of like you're doing it backwards, right? So the difference is like it's decreasing. This becomes minus 13, minus 11, minus 9, right? And so the difference between them, between these two like flat lines, is actually going to be decreasing, because we were decreasing going backwards because we're square rooting and not squaring. So it is going to be a straight line between 2 and 3, but it's going to be less than the difference between these two. Okay, you can kind of just estimate it. So if you think about now the difference between square root 2 and square root 3, right? And then if you compare that, say the difference between square root 65 and square root 66, there's going to be a big difference between that decimal, right? And so between square root 65 and square root 66, those numbers are going to be much more closer to each other compared to square root 2 and square root 3. Okay, and this kind of pattern just repeats on, and it goes on like that forever, and it gets smaller and smaller. The gap gets smaller and smaller. Apologies for pausing the video like so often, because I'm just doing it so you don't hear the workers in the background. Anyways, I've kind of shown this here. Root 2 is approximately equal to root 3, and the same with root 4 and root 5. But root 36 compared to root 37, right? There's a much smaller difference between these two compared to these two, right? So this is more equal to each other than these two are equal to each other, and this is more equal to each other than this one is equal to each other, right? Anyways, yeah. So I'm saying this is the square root. This here is just the sum of the areas under the rectangles. So this plus this plus that plus that, and it goes on. Now if we try and generalize this, because then I just did it from 0 to 4, right? What have I done here? Okay, so I've just written it like this. I've said this is R1, R2, R3, and then this will go on, so R4, R5, R6, R7, all the way to the last one, A. Okay, now the difference between, say, R3 and R2, or R2 and R1, or R1 and 0, is just going to be 1, right? We've already seen that. The difference is always just going to be 1. Okay, so we can just say that R1 is 1, right? Now, if you look at this, if you just imagine this was our case when A equals 4, you're always going to have one less rectangle. So you're going to have A minus 1. So if A equals 4, right, you'd have 1, 2, 3, 4 rectangles. But this one isn't actually a rectangle. So you'll have 4 minus 1. You'll always exclude this first one. So, you know, it'll just be A minus 1 is the number of rectangles. Right, and their Y value, well, we've just drawn the graph of Y equals root floor X. So it's just going to be Y equals root, and then Rn, where n is just whatever the thing here is, right? It's not a floor because we can just take the first one here, and then it'll just won't be a floor. So we could just pick this to be some integer to get the height. Okay, and the area is just going to be the base times the height. The base obviously is just 1, and then the height is root R subscript n. Okay, so we can just say that this here is just going to be the sum of 1 multiplied by R subscript n all the way up to A, right? So from n equals 0 all the way up to A, and then we're going to be summing up the area. This is the area. Okay, so the sum of areas is this. Now, we've actually got A minus 1 rectangles, not A rectangles. And so, oh, by the way, I've also said that instead of starting at n equals 0, I've started at n equals 1. The reason is because we're not actually including this one here. So if we just start n equals 1, it's the same. And then what I thought to do was, well, here we want a 0 at the bottom. So what I did was, well, if I decrease this by 1, that means I have to decrease this by 1 as well to have the same number of rectangles. So that's what I did. So I just decreased both of them by 1 to get this. And then this is basically the same as that, but the only difference is that I've just chosen different things to call these. So I've just changed it back to what they wanted, and you'll get that as your final answer. Similar thing here. So we're going to want to find this, right? We're going to have to sketch 2 to the power of floor x, and we want to show that it's equal to this. So I did a table of values, so you can go through and just work that out for yourself. So starting off by sketching 2 to the power of floor x in order to evaluate this, you can just do a table of values again. I think I've already shown this. Yeah. Okay. Yeah, it's just because I had to pause because of something. Anyways, so say if we go between 0 and 1, right, it looks something like this. If you just imagine like 2 to the power of 0, right, because between 0 and 1 exclusive 1, it'll just be 2 to the power of 0, so this will all just be 1. Okay, and now if we go between 1 and 2, exclusive 2, it'd be like 1.8 or something. It'll be 2 to the power of 1.8 or 1.9, something flawed, right? So it's just 2 to the power of 1, so this will be 2. And you can go through and then keep on doing the exact same thing. It'll look something like this, and as you notice, the gap between them will increase, right, and they'll go on forever. Now, this here is just the sum of the rectangles because it's just the area underneath the graph, right? And the number of rectangles is just going to be A. Okay, between 0 and A, so between 0 and 4 or A, you'll just have A rectangles, because in the other case, in this one here, you know, this first one wasn't even a rectangle, so you can't call it a rectangle. There was A minus 1 in this case, but here it's just A, obviously. Okay, do the same thing. I'm going to generalize it, call it this here, and then we'll do the same thing with the width always being 1. Okay, and then 2 to the power of Rn, whatever this R value is. So 2 to the power of, say, like 0.9 would give us this height here. Same thing here. So 2 to the power of Rn will be the height of any one rectangle. Okay, this multiplied by this will give us the area. Okay, and so we're going to sum the area from n equals 0 to A. Okay. Now, I've changed this a little bit. I've just to make it a bit simpler, I've said that this is 2 to the power of n. Okay, this was just a more generalized form, but these two mean the exact same thing because I've just said that they are the exact same thing. But the problem with this one here is when you think to yourself, when you're looking at this graph, right? Say we've got like 2 to the power of 0, right, to get the first height or the first area, which is the same thing, right? 2 to the power of 0 refers to the triangle, it refers to the rectangle in front of it. And then 2 to the power of 1 will refer to the rectangle in front of that. Then 2 to the power of 2 will refer to the rectangle in front of that. But when you get to 2 to the power of A, that's going to refer to the rectangle after x equals A, right? And we don't want that. So what we've done is we've actually counted an extra area, which is 2 to the power of A. So what I'm going to do is just subtract that back off. Okay? And that's fine. That's what we want. Now, if we're looking at just this sequence here, what I've done is I've just written it out like this. Okay? And I've called it UN. Okay, and it's got ratio 2. And if you realize here, this is actually just a geometric sequence with common ratio 2. Okay, so I'm going to use the exact same method that I did from the prep, right? Using common ratio 2. So I'm going to multiply by the common ratio. So 2 UN will give you this, right? And then 2 UN, that's the same as adding 2 to the power of 0 and then subtracting 2 to the power of A plus 1, right? And that will get us UN. You'll get that. Just rearrange, and you'll get u to the n. Sorry, u lowercase n is this, right? Subtract un from both sides. This becomes 1, and then this becomes 2 to the a plus 1 when you bring it to that side, and then minus 1. So you'll get this. And you look to yourself here, and then you realize, okay, well, this is not the exact same as this. So what's the problem? Well, it's because we had this minus 2 to the power of a, because this entire sequence was just this part here. Okay, so subtract minus 2 to the a to get the area. I've just grouped these together to group these two together. So this is 2 to the power of a multiplied by 2, and this is just obviously 2 to the power of a. And then I factorized out 2 to the power of a to get this. 2 minus 1 is 1, so this becomes 2 to the power of a minus 1, which is what we wanted to show. Now, determining an expression for this when a is positive but not an integer is, well, if you think about this, okay, so we've got this here, and we had this this curve that we drew. Now, this distance here is just 1, and then 1, and then 1, and then it'll just go on for 1 forever. It'll have width of 1. But when you get to the end, right, you'll have like a width which isn't 1. It's going to be less than 1, right? Because say if we had 6.8, well, we're going to have 6 widths of 1, and then we'll have 0.8. Okay, so the last width, the last base of the last triangle, the base of the last triangle is not going to be 1. It's going to be less than 1, and the exact values is that it's going to be a subtract floor a. right? And that what that does, if you think about it intuitively, is it just gives you the decimal, right? And that decimal is the width. You might just want to think about that for a little bit, but that's the base of the last triangle. And then the height of the last triangle is just this, obviously. Okay, so because obviously this refers to the triangle in front of it, that still gets us to A. Okay, and then multiply these two together to get the area of that. Is that what I've done? Okay, no, not yet. Oh yeah, never mind. Okay, I'm just showing this. Yeah, so this here is just this. Okay, and then we're going to add on this here is just the same as if A was an integer. Okay, and then we're going to add on the last rectangle, which refers to when A isn't an integer. So that part there. You can simplify that if you want. I'm not going to bother. Wait, can you even simplify that? Yeah, you maybe can. Yeah, you could factor out 2 to the power of floor A, but you don't need to. It doesn't ask. Anyways, that's the step question done. Those were really nice questions, by the way. I really like this this question. Anyways, I did leave what number it was at the top. Yeah, so it's 2004 step 1 question 2. If you want to look over it. Now, this one down question is very long, but basically there are these 4 people here: Arthur, Brenda, I think this is Chandrima or Chandrima, I'm not too sure. Sorry, yeah, 3 people together in an orangutan, right? And they're shipwrecked, right? They've got a pile of N bananas, big N, okay? And Arthur wakes up, he splits up the pile into 3 piles of bananas, okay? But then he realizes, oh, there's one left over. Okay, so what he does is he takes 1 pile for himself of those 3, and then he leaves that 1 extra banana for the orangutan. And then Brenda does the same thing, and then Chandrima does the same thing. Okay, after Chandrima takes hair share, so after Arthur's woken up and then reduced the total N by taking his third, and then plus that 1 for the orangutan, and Brenda does the same thing, and Chandrima does the same thing, we've got bananas left. Well, we've got, what they've done is they've woken up and then they've split the remaining bananas into 3 equal shares of M, with 1 left over for the orangutan. So after Chandrima takes her share, there'll be 3M plus 1 bananas left, right? It's going to be in the form 3M plus 1 because we've got 3 groups of M, and then we have plus 1 left over for the orangutan, so it's going to be 3 lots of M plus the 1 for the orangutan, so you get this. Okay, now Arthur's going to take a third lots of N minus 1. And the reason why it's N minus 1 is because we know that there's going to be 1 left over for the orangutan, right? And if we just did 1/3 N, which we could technically do, we're going to have this number here be a decimal, but you can't have a decimal number of bananas. So if we take away 1 from the total number of bananas and we take a third of that, that's going to be Arthur's share. So that's how much Arthur has taken, right? Plus 1 for the orangutan, right? And so we've got this as an integer, and we've got this as an integer. So we've split up 1/3 N, which would have given us a decimal, into an integer and an integer. And you could use the floor function that we just learned in the previous parts of this assignment, but I chose not to. Okay, and so if we do the total number of bananas N, subtract this, which is what's being taken, where the red is for the orangutan's share, you'll get how much is left, which is that, and that simplifies to this. Okay, Brenda does the same thing. But remember, with Brenda, there's going to be 1 leftover banana for the orangutan. So she's going to take 1/3 of this, but minus 1, right? So that we have an integer, and then we're going to plus 1 after it for the orangutan that she's left. 1 for the orangutan that she's left. Okay, and then we'll do this, which is the last total, subtract this, which is what's being taken, to get what's left, which is that, and that simplifies down to this. And we'll do the same thing with Chandrima. So she takes a third of this. So Chandrima takes 1/3 of this, right? But minus 1, because if we didn't minus 1, then it wouldn't be an integer, right? Remember, we do the minus 1 because we know that there's going to be 1 left over. So say, for example, this was 31, and she takes a third of 31 plus 1 left over for the monkey, for the orangutan, sorry. If we do 1/3 of 30 minus 1, so 1/3 of 31 minus 1, so 1/3 of 30, which is 10, and then minus 1. No, sorry, and then plus 1 for the orangutan. So you have this is her share, which is an integer, and then plus the orangutan's share. That's how much is taken. This was how much was left before, so you do this, take away this to get what the new total is, which you'll get as this. But we know that after Kandrima takes her share, there's going to be 3m plus 1 bananas. So if we set these two equal to each other, you'll get this. Just rearrange and you'll get that, and that's fine. Show that if n satisfies this for some integer m, then n plus 81 also satisfies it for a different value of m. Now what I did was, I said, okay, well let's replace n with n plus 81, and then let's replace m with km, where k is just some multiple of m, right, where k isn't 1. Okay, because this km is going to be the new value of m. Okay, expand this, and I brought this to that other side, and then I said, well, a10 here, they're the same thing, so we'll just make them equal to each other. You'll get that, and then I rearranged for km, which I got as this. And remember, this km is the new value of m for this different value of m, so I'm going to plug this into there. Okay, so I'm going to plug this into there to get that, and that's fine. Right, when n equals n plus 81, it satisfies it for a different value of m, which is 8 plus m. Okay, that's fine there. Now, if n equals minus 2 is a solution, there exists an integer m such that 8n plus 81m plus 65. Never mind. Yeah, find a solution for a positive number of real bananas. We know that one solution is n equals minus 2. So I plugged in n equals minus 2, and then I rearranged to get m equals minus 1. This is a solution, because it is an integer technically, so that is fine, but we want a positive solution, right? So this is one of the solutions. We want a positive solution for n. I wrote it as this, so a10 take away 65 is equivalent to 0 mod 81. And what I'm saying here is I've just kind of rearranged this, and I've said that, well, we want say you've got this, we want n to be an integer, right? So a10 take away 65, when you divide that by 81, we should get an integer answer, right? So that's my idea. Now, a cool trick that you can do with stuff like this is you could just add 81 continuously, right? You could just add whatever the mod is. Okay, hopefully you understand this step here. But what I'm saying here is that a10 take away 65 divided by 81 will not have a remainder. So this means it has a remainder 0. Therefore, it's an integer. Okay, so I added 81 to both sides. You don't actually have to add it to this side. Ignore what I just said. You don't have to add it to this side because this is modular arithmetic. So you could just add it onto one side. It's fine to do that. Right, and then I solved for n there. N there would equal minus 2. I added so I realized, well, if I keep on adding 81, this is going to be positive, and when I bring it to that side, I'm going to have a negative value for n. So instead, I should take away 81. So I went back to this and I took away 81 to get this. I solved for n. It wasn't an integer, right? So I took away 81 again, took away 81 again. Oh, never mind, yeah. So I got to that final solution, and then when you rearrange that, you get n is congruent to 79, or n equals 79. So n plus 81 is always a solution, right? Sorry, no, that's separate. Yeah, so n equals 79 is the positive solution. Now, I did this method, and then I realized, wait a minute, you don't get a calculator for these assignments. So there is a new way, there is a different way to do this, which is actually much better. Now, remember, we said that n plus 81, where is it? Here. n plus 81 is always a solution, and it gives us a different value of m. But the important thing here is that they're both integers, so that's fine. So if we know that n equals minus 2 is a solution, and n plus 81 is always a solution, so you could say that minus 2 plus 81 is a solution, which gets you 79 too. So, just be smart about it, and just do this. It was really dumb of me to actually do this, but it's just what came to my mind first, for some reason, even though this is very explicit and obvious. Anyways, we want to find a general formula for n and m, that satisfy this. So if n plus 81 is always a solution, right, so is minus 2 and 79. We've already gotten those as solutions. And if n plus 81 is always a solution, as I've just said, we can plug this in there and then get a new solution that's always correct. And then plug this into there, that gets a new solution that's always correct. And then plug that solution back into there. So it's a recursive relationship. So you could write this as like n subscript p plus 1 equals n subscript p plus 81, right? So 79 plus 81 is a solution, which gets you 160, and then 160 plus 81 is also a solution. You know, and that goes on forever. And in general, you could write that as 79 plus 81k, right? But we can do better than that because, you know, we've for some reason we've chosen to start at this second solution, but we could have chosen to start at this one too, right? So minus 2 plus 81k is also a solution that you could choose. Okay, and if you think about it, well, say the 0th solution, which would be this one, when k equals 0, you'll get minus 2, and then when k equals 1, you'll get this next solution. When k equals 2, you'll get this solution. When k equals 3, you'll get, you know, 240, whatever 81 times 243 minus 2, so 241 is the next solution for n. And so you could just write n as minus 2 plus 81k, and if we plug this into there or there, it doesn't really matter, you'll get m is 8k minus 1 when you rearrange. This is kind of long to expand and rearrange, but you know, you'll eventually get this, and that's your final answer. Anyways, thank you for watching.